Okay, so now I have some slides that are going to go over more the like less administrative, more real-time operating systems. What a real-time operating system is, why you should care about them, and how we're going to use them. So I'm going to give you also a bit of an introduction to microcontroller basics, although we won't use them. It would be worthwhile for you to invest a bit of time informing yourself about them. If the exam does happen, I won't make it very heavily, I'll make it a very large part of the exam, as it would be unfair, but it would be good if you could just sort of take on board some of the microcontroller stuff, as it is an embedded systems course. So, what is an embedded system? So normally an embedded system is part of a larger system in that it does some sort of a dedicated job that a good example, right, is in a car, you have a brake controller or something. It is responsible for actuating the brakes, and it is part of the entire system that is the car. It does one thing, and unlike our computers, like our laptops, it's not generally not reconfigured to do something else. It will do one thing its entire life. And so then we get into this sort of realm of real-time embedded systems. And real-time embedded systems generally involve things such as real-time programming. So this means that the code itself, or the program, meaning the system, needs to have some sort of feel of time. Like in this case, I worded it saying it has to be predictable and it has to be able to satisfy timing requirements. And to satisfy timing requirements, you have to make sure that you've written your code using paradigms or methods or programming languages or operating systems that are able to have an awareness of time and to include these important timing constraints and whatnot into your code, so that when you run it, they can run with respect to real time. So this is the most important thing, is that it's code that has an awareness of time, and you can give it deadlines, essentially. One thing that people think is that real-time systems are just very fast systems, but real-time doesn't mean that it's quick. You might have a real-time system that needs to read the temperature of a pot plant, of a plant, to make sure it's getting watered. It doesn't need to get updated hundreds of times a second. It's probably okay if it gets updated once every 10 minutes, right? But for some reason, it's important to know that it happens every 10 minutes. Then it's not quick, but it needs to have this sort of predictable guarantee that every 10 minutes you'll get the temperature, right? So time requirements. Now, the thing that makes real-time programming very tricky and very difficult is the fact that embedded systems are generally, a large amount of embedded systems are used in sensors, actuators, in some sort of an environment that interacts with the physical world, right? So a temperature sensor or a brake controller, these things are interacting with the world, which is pretty much, it's not pretty much, it's very hard to model or to make predictable, right? And as such, it's very hard to model response times, or worst case response times, for embedded systems that are impacted by the real world. And this means that when you want to create requirements for worst case behaviors, as I've said here, you need to do analysis to make sure that the flight controller on your Boeing is going to be a bit more reliable, or make sure it's never going to fail. Because if a flight controller fails, then you can have loss of life. You really need to make sure that certain real-time embedded systems are very predictable, they're very deterministic, and to do this, you need to have analysis methods that trying to model or analyze interactions with the physical world, which is extremely complex, right? So this is the challenge. Examples, as I mentioned before, you've got planes, cars, factories, sensors, sort of things, communications. I mean, like on our phones, we will also have things like the DSP, like digital signal processor, which will, like, if I say to my phone, like, okay, Google, it will wake up and whatever. And these are all like little embedded systems. Sound processing, computer games, like what we would normally implement in this course would be an embedded system. So these and these systems are real-time systems because all of these in some way are impacted by time, right? So a computer game has frames that it needs to meet. Like a game that spits out 3 frames a second is not a playable computer game. These control systems are a little more self-explanatory. I mean, if you press the brakes in your car, you want it to stop. So the things that make real-time systems in the case of embedded systems, or like the typical properties of them, and the things that present challenges, let's say, in developing these systems are, one sec. So in general, embedded system is a very resource-constrained device. So this is not a problem that we're going to be presented with this semester, as we are developing on x86 laptops with gigabytes of memory, and we don't have to worry about the kilobytes, tens of kilobytes. But the students that would normally run this course or do this course on these embedded boards, if they wanted to use bitmap images for their games to add sort of like a bit of flair to it, they would really have to worry about how large each individual image is, because they would quickly run out of RAM, right? And so similarly in control systems and whatnot, you really have to make sure that if you have sort of large complex digital signal filters and stuff, that you have enough resources, or your resources are quick enough that you can actually handle the required work. In these sort of sensor fields, obviously you have a continuous interaction, so that your embedded system plays sort of like the role of sort of like a transfer function. It takes in some sensor value, it performs something, and it will send out a signal, send out comms, actuate something, whatnot. And more today's day and age, you'll find that embedded systems can actually start to multitask, because you can get multi-processor embedded systems. And so, for instance, a CCTV camera that is performing person recognition, like on the camera itself, can multi-thread the image processing. And so you need to make sure that you have all these tasks, and maybe something that's less parallelized, but simply just you have different tasks responsible for different things on the system, that these things run simultaneously, and that they can be managed in a way that you are respecting, like synchronization, shared resources, and all of these sort of things. Because if you are, for instance, doing unsafe access to shared resources, then you are going to have a very unstable system. And in safety critical applications, this could be significant, and loss of life, system failure. I mean, it can be really bad. I mean, plane crashes happen because of failing embedded systems. I mean, it can be a very serious field. So this is the sort of general, as I was saying before, this sort of transfer function, let's say, like function, like you have some sort of an environmental input, and then you'll have a like your embedded system, your program, real time, like in this example is a brake controller, and then it is actually enabling the actuator. So it sort of takes in a signal, processes it in real time in regard to some sort of constraints, and then it will enable the actuator, right? So when I talk about now, like obviously I've been mentioning in the last few minutes this sort of importance of respecting bounds, system failure and whatnot, and there are a few key terms that are really important for classifying these sort of real-time systems, giving, the two important ones that classify is sort of like how important deadlines are, right? So you have a hard real-time system, and this is a system where the response of the system for a given deadline, like the deadline must be met. So a brake controller, if you push the pedal, you have to guarantee that within 10 milliseconds, whatever the deadline is, that the actuator has been actuated, right? You can't say, oh, if it doesn't happen, it's okay, we'll just try again. No, because that's probably going to lead to a system failure, like a car crash. But a soft real-time system says that the deadline doesn't have to be met. I mean, it's good if it's met. Obviously, you always want to try and meet a deadline, but if you're running a really hard computer-intensive game on an old laptop, and then your laptop can't make the frame rate of 60 FPS, it will just reduce the frame rate and it will try its best. But if it can't meet the deadline, then that's it. Its system doesn't fail, no one dies, the laptop doesn't blow up, the user experience just deteriorates. Shared resources. So this is somewhat of a real-time programming word, but just as much, it's more belonging to like multi-threaded programming, in that if you have memory or an IO port or something and you have multiple tasks that are accessing it, you need to have like the resource itself, like the memory, has to be shared between the tasks in a way that's safe, but also things that make sure that the data isn't invalid, like you're not serving old data, like your brake controller is not actually turning the brakes on based off of the last press. Like you want to have the most recent data. And then this is also sort of comes together with concurrent access. If two things want to use the resource at the same time, that there's some way of managing how these two tasks actually get access to this, such that you don't have undefined behavior or you're not using invalid data. So going back to the sort of hard real-time or deadlines, there are two sort of important terms that come up, and these are very important. I mean, these are pretty much guaranteed exam questions. There's the worst case execution time and the worst case response time. So one of them actually builds on the other one, meaning that the response time builds on top of the execution time. And so the execution time is, as it says, it's the time that the system takes to execute some function, right? So how long it would take a brake controller to turn the brakes on once it gets a signal. That's the execution time, like of input to a task that turns on the brakes to when the brakes go on. But the response time is the longest time that the system needs to finish reacting to the input. Like if you know about interrupts, or just the basic idea of interrupts is that some other task can interrupt the system at any point in time. So there are these variable delays that can be added to the execution of some process based on other factors. And so the response time is the worst case, like the absolute, like all these interrupting factors happening. What is the longest time that some task would take to execute based on all these factors? Whereas the execution time is just this one task executing. The response time is the entire system getting interrupted and whatnot, and how long it takes the system to respond to some input, given worst case scenarios, like every interrupt happening, everything going worst it can possibly can. So as you can imagine, in flight controllers and in these sort of like really hard real-time systems, there are deadlines that cannot be violated. We need to know, or need to be able to say, these deadlines will be met. Like this brake controller will actuate the brakes. This flight controller won't fail. It will meet this deadline. But how do you know this? How can you say with certainty, we can use this flight controller without risking significant loss of life? And so you get into this field of analysis, of like program analysis, timing analysis, hardware modeling, whatnot. But it's really hard to model this because there's such complex systems. The hardware itself is super complex. The code can be large and have lots of different possible branches of execution. So how, if you put such a complex code model on top of a super complex hardware model, how can you be certain that you will meet a deadline? And really, you can't. I mean, it's a problem that is beyond the computational abilities of our modern time. But so there are essentially what we need to do is we need to provide a certain percent, like we need to say with a certain amount of certainty. This is why planes still do crash. I mean, why things do fail, because there's always the 0.0000001% chance of a system failing. These things do exist, but we need to be able to analyze our system and say to a certain degree of certainty, we will always meet our deadlines. And so this can be extremely hard because of all the different things involved. And as such, there's a lot of different methods, but mainly it comes down to statistical modeling. So the reasons why, as I mentioned before, you have these complex hardwares, but what are the actual specific things that can influence the predictability or the real-time behavior of a system? So you have a crystal clock on a board that oscillates at a certain frequency. Now, ideally, this 72 megahertz clock oscillates exactly 72 million times per second without fail all the time, but it doesn't. And this is when you get a thing called clock drift, where the clock doesn't hit the exact amount of cycles in the time it should, and as such, obviously, the clock's value is not completely accurate, and as such, your concept of time is not completely accurate, right? Processing models, whether you can actually model every single possible execution that the model can take. I mean, if you have for loops, with variable length, it's hard to model all of the possible executions of a varying or a dynamic loop, and how do you then model all of these possible execution paths of these what can be extremely complex, multitask, multi-threaded programs? This becomes very unrealistic and impossible. So then as well, you have the compiling of the code, and you have your code that's compiled to a certain system, and how do you guarantee that when you're compiling your code that certain machine code instructions will come out. There's a lot of different sorts of optimizations that are applied, transformations, things that are done by the compiler, and these are also very hard to control. All of this compiled on top of each other, on top of the sort of algorithms that are used in the program itself, creates extremely complex models based on top of complex models, and you get this sort of stack of extremely complex things to model that the whole picture is just... Anyway, so this formal verification, which is where you say to a certain degree of certainty this system is stable, is deterministic, your deadlines will be met. This is usually done by very complex tooling, and it's also a very active field of research because it's very important to certain industries, specifically control systems, automation, these sorts of fields, robotics. So if predicting this stuff is so complex, I've sort of covered this slide already, we need to have this deterministic computing. And the problem is, it's not feasible really. So the solutions that we have, there are a few different solutions, because if you take, for example, here, like our classic PCs, they don't really have any awareness of time. My laptop does know roughly what the time is, but it's not intrinsically aware of the time. It doesn't perform code. It doesn't run my PowerPoint PDF thing in regards to time. It just wants to try and update the screen as quickly as possible, but it's not saying the screen needs to be updated within 10 milliseconds or the laptop explodes. It's just not important, right? So the solutions to this are a few different ones. There's low-level bare metal code, meaning on an embedded system, on the microcontroller, you can write code that's extremely minimal and extremely low to the hardware. And if the lower you get to the hardware, the easier it is to model the system, to model the execution. The more simple your program, obviously the simpler it is to analyze. This is not usually feasible, as it sort of limits the functionality, and also the development time is a lot harder and it's a lot more expensive, because writing code on the hardware at such a low level is very slow and very labor intensive. Whereas things using libraries and all these things, they increase they speed up development time, but as a result, they add abstraction, and they make this analysis process harder. Other ways that you can sort of tackle it, one of them I'm very familiar with, one of them I'm not very familiar with, and we're focusing on one of them and not the other. So real-time operating systems, such as FreeRTOS, which this course is based around, is an operating system that has an intrinsic awareness of time built into it. Meaning that you can create tasks, that you can delay, that you can set sort of timing requirements for, you have time control built into everything you do, right? Or you have real-time programming languages which do work in a very similar way, and that you can specify timing constraints and sort of intrinsically add timing into your program, but they don't work on the same way as operating systems do, because an operating system is more like a managing of tasks, scheduling, memory management, this sort of thing. I don't really have too much experience with real-time programming languages. I just don't want to say they exist. We won't really touch on them at all in this course. We're focused on real-time operating systems, because real-time operating systems, especially in the less safety-critical field of embedded systems, are very common. Like FreeRTOS is it's seen a lot in the industry and everywhere. So it's a really good thing to sort of get used to. So this bare metal code I was saying, it gets you down to the hardware. I've pretty much summarized this already, but it's where have I written it here somewhere? No, here. Disadvantage, I didn't write it in. So expensive, pretty much, because development time is generally quite large, right? Programming languages, I've said this all again, I should have gone through the slides first. So this is where we land at, and this is where I really need to sort of get, where we need to focus. So an operating system, I think this will probably come up later in the slides, but an operating system, or the core components of an operating system, not just FreeRTOS, but also our computers, servers, our phones, all of them, like the core thing that they need to do is manage jobs like multitasking, manage memory. So we have tasks, resource management. So resource management is memory. And then you also have sort of like these timing things. So this timing is part of the real time. So you need to make sure that the OS provides predictable timing and scheduling. So the scheduling happens slightly different on a FreeRTOS embedded system than it would on our laptops. Our laptops sort of want to make sure that all the tasks get the same sort of CPU time, but a real-time system like a FreeRTOS embedded system wants to make sure that the tasks that need to meet their deadlines, like the really high priority task with a fixed deadline coming up quickly, need to meet them. So they will schedule with different algorithms, with different priorities, and so we'll come into this in a bit later. But operating systems, not just real-time ones, but just in general, they also need to manage inter-process communication. So when one task finishes with its work and it needs to send a message to another task saying it's finished, this transferring of message between tasks is handled by the operating system. Similarly, the resources, like if two tasks need to use the same region of memory, the management of these resources is also done by the operating system. But this is not just, these couple of things are not specific to real-time operating systems, but real-time operating systems also add on top of this real-time constraints, meaning if I want to send a message from this task to this task, it needs to happen within a certain time. So you can implement or impose timing constraints on top of most components of the operating system. So this is slightly like an extension of what most operating systems like Linux would do, is that they sort of, like real-time operating systems add this timing component, hence real-time, right? So the why you would use a real-time operating system in a project that's probably not safety critical, I mean, such as like where you use programming a game, is that it makes the development of these systems very easy. So like this here, if I want to create multiple tasks at a low level running bare metal code, you would have to write a lot of code to manage context switches on the CPU, which is intrinsically handled by the operating system. And as such, as a developer, if I want two tasks, I just create two tasks using two function calls to, like for instance in FreeRTOS, X task create, boom, 2 tasks, easy. So it's very easy. My code, like the complexity of my code that I'm writing is becoming a lot less, and as such, development cycle is quicker, and it's easier to implement things, becomes cheaper, blah, blah, blah. Similarly to the actual complexity of the code, developing more complex systems, meaning more tasks, becomes a lot easier for the average engineer to implement, right? So I am able to create more tasks without having to really know the ins and outs of CPU context switching, right? So it's this abstraction, like in all programming, and as you get up to sort of like the higher level languages like Java, the more abstracted you get, the easier it is to write code, but generally the less efficient. So like operating systems or real-time operating systems like FreeRTOS are not as efficient as writing bare metal code, but the trade-off is that the development process is a lot quicker and a lot easier, right? So disadvantages that with this abstraction, you obviously get more undefined, or more like the behavior is harder to define, if not impossible to define, and as such formal analysis becomes more difficult. Similarly, with other higher level languages, the more abstraction you add, the more overhead you generally add, and therefore the slower your code is. So while a FreeRTOS system written in C is going to be miles quicker than some web app written in Node or something, compared to writing machine code or assemblies directly onto a CPU, it is still slower, right? So now going back to soft real-time, as I mentioned, there's soft real-time and hard real-time. So we are specifically interested in soft real-time in this course because we can't really have you programming hard real-time systems because the complexity is beyond the scope of a bachelor course, and it's probably just not as much fun. So a soft real-time, like a very good example, and something that we will be doing is a computer game, right? So our deadline is our frames per second, our FPS. A nice smooth game runs at 60 FPS. If your system can't handle it, will get down, like your FPS will get down, and you'll get this sort of stuttering, right? And these artifacts that don't lead to a good experience. But if the deadline is missed and the frame rate goes down, no one's dying. The user experience goes down. And this is why it's called soft real-time, because we don't really care. Of course, we want it to be as high as possible, but we don't really care if we get a few less frames, right? So generally, just a bit of background into how frame rates in computer games are generated. As I do a lot of research in power optimizations for like mobile devices, essentially, where the FPS is sort of like my the thing I want to optimize for. The frame rate comes from the screen, or like this signal. You have like a VSync or a sync signal where the screen says, hey man, I can handle up to 60 FPS, and each time it's presented the new screen, it'll send a signal asking for the next frame, essentially. So when the rendering is finished, it will the frame will be calculated and rendered, and then the monitor will send the signal and it will send the frame, right? But the problem can be that if this is your sync signals coming in here, as we can see, if you have some sort of a CPU load that you're calculating that goes longer than the sync signal, you won't have the frame ready to send to the monitor by the time the next sync signal arrives. And your sync signal in this case is your deadline. It happens 60 times a second, and it provides you with the period, like the time you have to work with to meet your deadline. So this is here an example of a deadline miss, in that this CPU, like this orange bit here, took too long that it missed the deadline of the VSync signal, and as such the GPU process took too long, and as such we actually end up with the same frame being sent twice. So this is when the frame rate actually drops. So when you have a game on your computer and your laptop can't handle it, you are actually still getting 60 FPS, but you're getting multiple of certain frames because the new frame wasn't there ready to be rendered, so the old frame was shown again. As you can see here, you get these 2 frames that are the same. You're getting the 1 frame twice, right? So That's essentially the soft real time in terms of computer games, in terms of refreshing of displays based off of this sync signal, which is our deadline, right? So I've got one last bit to go through, and I will go through. It turns out my camera can only record at maximum half an hour, but luckily I just finished that lecture on the half-hour mark. So anyway, I'm going to quickly take a break, and I'm going to do the last section, which goes over the lab setup, which is somewhat applicable, somewhat not, and some embedded system stuff. So this is sort of theory that you won't really get hands-on with, unfortunately, this semester, but it's good to know anyway. So last one coming up, and that will wrap up the introductory lecture. After that will come a Git lecture, which I will hopefully record tomorrow, and I'll upload this all at once, so you'll have a lot of lectures to watch and to guarantee that you won't have to leave the house this week.